Hi, this is Dr. B, and in this experiment, let's compare the energetics of methanol, which is this stuff here. Notice it's a clear, colorless liquid, to ethanol, which I have right here, also a clear, colorless liquid. What we'll do is use an equal amount of each one and heat up some water with it. Let's see which one can make the water hotter under equal conditions. But first, let's talk a little bit about methanol and ethanol. Here's the structure of methanol here. I hope you can see that it is a one-carbon alcohol. And here's the structure of ethanol here. It's a two-carbon alcohol. We could call this CH4O. Notice it's alphabetical if you count up how many of each atom we have. And here we have 2 carbons, 6 hydrogens, and an oxygen. Either way, we're going to burn it. Also, as long as we're on it, do you notice that every carbon has 4 lines attached to it? We call those bonds. Do you notice that each hydrogen has 1 bond? And each oxygen, we draw this cleanly, has 2 bonds. Nitrogen has 4. Honk if you love chemistry. H-O-N-C, 1, 2, 3, 4. Now when we burn it, and we will, each one will combine with oxygen, and it will make carbon dioxide and water. I want you to think about these things when they are burning, right? One is probably going to get hotter than the other. Think about the bonds that might be broken. Think about the bonds that might be formed, right? Oxygen forms 2 bonds. It looks like that. Carbon dioxide, the carbons form 4 bonds. The oxygens form 2. It looks like that. And water obeys the same rules. 2 bonds for the oxygen, 1 bond for the hydrogen, and it looks like that. So maybe you'll be thinking about what bonds are being broken, what bonds are being made, which ones require energy, which ones release energy, and there you go. Okay, so let's do the same thing for our ethanol, and we'll think about the ratio that they combine. If you've already learned how to balance chemical reactions, this is a good opportunity to pause the video and just do it on your own here and compare it to how I do it. When I do it, I'm noticing we start with 1 carbon, we end with 1. We are balanced with respect to carbon. We have 4 hydrogens here and 2 there. I mean, I could try making that H4O, but that's no longer water. Why don't I make 2 pairs of hydrogen atoms? 2 times 2 is 4. Imagine this being drawn twice, and you'll see that you have 4 hydrogens on this side and 4 hydrogens on this side. We started with 4. Once the reaction's over and produced products, we ended with 4. It's balanced with respect to hydrogens. Now, we do know how many oxygen atoms we're forming right here, so why don't we total those up and make it equal this side, recognizing that 1 is already accounted for, and if we change that number, it won't change our carbon and hydrogen and force us to start over. So, I think we have 2, right? Plus 2 times 1. This is not H2O2. So 2 plus 2 is 4 oxygens, which means 1 plus something doubled equals 4. Therefore, something doubled equals 3. Therefore, our temporary number is going to be 1.5. In order to make these whole numbers, let's double everything. This 1 becomes a 2. This 1.5 becomes a 3. This 1 becomes a 2. And that 2 becomes a 4. 2 to 3 to 2 to 4. Check your oxygens. I see 2 plus 6 equals 8. And here I have 4 plus 4 equals 8. You check them all. They should all work out. This must be burning in that ratio. These are getting all busted up. This is getting all busted up. These are forming 2 of these. These are forming 4 of those. Doing the same thing with ethanol. 2 carbons, we need 2 carbons, check. 6 hydrogens, how about 3 pairs? Check. Total oxygens, I see 2 pairs, meaning 4, plus the 3 singles, I have 7 oxygens. Oh, I like that, because 1 plus something doubled equals 7, something doubled equals 6. 3 should do it, and I don't have to double everything. 1 to 3 to 2 to 3. Quickly check our oxygens. 1 plus 6 is 7. 4 plus 3 equals 7. It looks good. It's balanced. This molecule is breaking up entirely. Notice we don't even have a carbon-carbon bond left. This is breaking up. These are forming. I just wanted to show that to get you thinking about what's happening when things burn on a molecular. Okay, let me show you what we have set up for the experiment. You should see 2 identical setups. On the left side, we're going to heat up water using methanol. On the right side, we're going to heat up water using ethanol. So methanol on this side, ethanol on this side. The setups are otherwise identical. The distance from the test tube to the weighing boat here is identical to this one. The amount of water is identical in each. The location is the same, so we should have good relative data. Okay, we're going to burn 1 ml of each. I do have a readout that we'll get so that we can show you. In fact, I think I can show you now. Let me just minimize this. And if you look at this screen, you should see that we have, there they are, 2 digital readouts for each one. Now, it shouldn't matter if they're a little bit different because the amount of energy required is the same regardless of your starting point, as long as you're in the liquid phase. So let's not worry about that. And let's see which one can heat up the water hotter. Okay, I've started collecting, as you can see here. And it's time to add our liquids and go ahead and heat it up. So I'm going to use 1 milliliter of each. These are graduated. So here's our methanol. One milliliter. Put it far away for safety. Here's our ethanol. Same amount. Make sure they're both centered. This far away for safety. And let's ignite them. Okay, they are burning. I'm going to move this around. Hopefully you can see it. Notice the difference in flame colors. You should also see a difference in flame time. And we are getting real-time telemetry over here. Let me get this out of the way. So they're getting hotter for sure. And I'll let you take a picture of that when it's done. The methanol is done. The ethanol is still burning, even though it's the same amount. And I'll let you watch the real-time telemetry here. The ethanol has just gone out. It should continue to still get higher. And we just need each one to hit a maximum point. Looks like 34 for the ethanol, and only about 27.5 for the methanol. They are starting to go down now. So let me move this slightly. Okay, we're setting up again for our second trial. We got the same thing. And here the initial temperatures are for the ethanol. We got 23.5. And for the methanol in blue, we've got 23.1 degrees Celsius. Okay, I've put exactly 1 milliliter of methanol on the left and 1 milliliter of ethanol on the right. And it's time to go ahead and light them up. There we go. They are burning. We are starting to get a temperature increase. And the methanol is nearly finished. You can see that. And it's out. Ethanol is still burning like before. And the ethanol is now out. Usually it slides up for a little bit longer. Let's wait till we get a plateau. I'm seeing 29.7 for the ethanol appears to be maxed out. And 26.9 for the blue methanol, which started to go down, so 26.9 was our max for the methanol. 29.7 is pretty clearly going to be our max for the ethanol. I'll just let it go down a tick just to be sure. There it goes. Okay, that's 2 good trials. Use that data to answer the questions, and thanks a lot. Level.